everyone! Today we are going to explain about X-ray photoelectron spectroscopy. Introduction. X-ray photoelectron spectroscopy (XPS) is a surface-sensitive quantitative spectroscopy technique that measures the elemental composition at the parts per thousand range, empirical formula, chemical state, and electronic state of the element exists within a material. It also based on Einstein's idea. The concept of photon was used to describe the injection of electrons from a surface when photons were impinged upon it. What is the advantages and disadvantages of X-ray photoelectron spectroscopy (XPS)? Advantages: it is non-destructive technique. It has surface-sensitive 10 to 100 amperage. Quantitative measurements are obtained, provides information about chemical bonding, and also elemental mapping. Disadvantages of X-ray photoelectron spectroscopy (XPS): it is very expensive technique, which is have a high vacuum is required, and also slow processing, which is half to 8 hours per sample. It also required large area analysis, and helium and hydrogen cannot be identified, and the data collection is slow, from 5 to 10 minutes.
Theoretical background of X-ray photoelectron spectroscopy.
X-rays are emitted onto the probe's surface. These photons eject the electrons from the inner shells, which is photoelectric effect. The ejected electrons have certain kinetic energies which are collected to analyze the chemical composition as well as the electronic structure. Following the previous process, the ion will be in an excited state. Hence, an upper shell's electrons falls and fills that hole in the K shell. To conserve the energy, another electron from the L shells absorbs the energy difference, which means it has now enough to escape and is emitted as an outer electron.
Setup of XP spectrometer.
Blue arrows indicates photo-emitted electrons from the surface. Electron collection lens collects electron emitted and bring to electron analyzer. Electron detector detects the types of electrons, concentration, and bonding of sample analyzed and presented on a spectrum.
How XP spectrometer works.
Firstly, high-energy X-ray is emitted to the surface and is absorbed by the atoms in the sample. Then, the atoms emitted will release excited electrons. This phenomenon is called a photoelectric effect. Then, excited electrons is emitted from the surface straight to the electron collection lens. Next, electron energy analyzer will analyze the properties of electrons in terms of its chemical bonding and concentration to determine the structure of atoms in the sample of interest. Lastly, electron detector will then change the signal into a spectrum that represents the characteristic of analyzed sample.
Instrumentation for XP spectroscopy. Surface analysis by XP spectroscopy requires irradiating a solid in an ultra-high vacuum UHV chamber with monoenergetic soft X-rays and analyzing the energies of the emitted electrons. XP spectroscopy need UHV to remove adsorbed gases from the sample, to eliminate absorption on contaminants on the sample, prevent arcing and high voltage breakdown, and to increase the mean free path for electrons, ions, and photons.
Spectra analysis.
This figure shows the XPS spectrum of a palladium probe. On the left side, the intensity is represented with respect to the kinetic energy, and on the right side with respect to the binding energy. A photoelectron spectrum is recorded by counting ejected electrons of a range of electron kinetic energies. Peaks appear in the spectrum from atoms emitting electrons of a particular characteristic energy. The energies and intensities of the photoelectron peaks enable identification and quantification of all surface elements. This allows elements on the surface to be identified based on the unique binding energy each element has. The peak areas on the spectra can also be used to obtain the concentration of the elements on the surface. The area under peak in the spectrum is a measure of the relative amount of the element represented by that peak. The energy axis is inverse due to obtain a clear view representative of the atom structure. So the more you approach the nuclei or the origin, the higher the bond energy is going to be. At the right side, which is binding energy figure, the emission from the 3D levels give the most intense peak, and it is at a binding energy of around 330 electron volts. In addition, the 3p and 3s levels with peaks at around 550 electron volts and 670 electron volts respectively. The height of the peaks is an indication of how many electrons there are in that energy level.
Chemical shift.
In compounds where ionic or covalent bonding occurs, the peak position might shift. If we analyze a molecule, we will get binding energies as well. As you can see, in this titanium and titanium dioxide comparison, the binding energies will shift as new bonds form. In this example, we have an oxidation which shifts the binding energy by around 5 electron volts to the left. So, what you need to take away from today is basically how the XPS theoretically works and how to interpret the data of such a spectrum.
Examples and uses of analyzed material in SPS spectroscopy. Materials issue analyzed with SPS include surface segregation, corrosion, semiconductors, and electrical contamination, surface cleanliness, paint and coating delamination, and intergranular fracture. Examples of analyzed materials: coating failure. SPS is well suited to the study of coating failures. Analysis of the exposed material interface delineates the true location of dispersion. Comparison of the surface to the bulk materials often shows the presence of contaminants. In these examples, SPS determined that a fluoride-contained glass surface was contaminated with a high level of Teflon, preventing ultimate coating adhesion. The base glass contained fluoride compound, polytetrafluoroethylene, is a synthetic fluoropolymer most well known by the DuPont brand name Teflon with many applications. SPS can easily differentiate between the fluorine state of a simple fluoride and fluoropolymer. Polymer technology. SPS has many applications in polymer technology. One application is the study of polymer film before and after surface treatment processes, including plasma treatment and corona discharge treatment. The data compare that the carbon oxidation state of untreated and treated polyethylene after discharge treatment in air. Shifting in the carbon SPS peaks indicates different binding states are present. The adhesive polyethylene is predominantly alkene carbon. Carbon oxygen body is clearly present after the discharge process. Uses of analyzed materials in SPS spectroscopy. SPS is used to measure elemental composition of the surface, empirical formula of the pure materials, chemical for electronic states of each element in the surface, uniformity of composition across the top surface, line profiling, uniformity of elemental composition as a function of an ion beam etching, depth profiling. It's routinely used to analyze inorganic compound, metal alloys, semiconductors, polymers, catalysts, glasses, ceramics, paints.